Have you ever looked at a big industrial plant, with all those pipes going everywhere? It looks like a total mess, just a chaotic metal jungle. But here's the thing. Hidden inside all that chaos is some seriously brilliant engineering. It's all designed to control these invisible forces that could literally tear the whole place apart. So, let's dive in and uncover the secret genius behind all those bent pipes.
I mean, it's a fair question, right? A straight line is the shortest path. It'd be cheaper, way easier to build, and you'd use a lot less material. So why on earth do engineers go through all the trouble of adding these weird loops and bends and zigzags? Believe it or not, this wasn't always common knowledge. Before we had powerful computers, figuring this stuff out was basically a dark art. People actually called it a mysterious subject. You had just a handful of super specialized engineers who could do the math, and it would take them weeks of nonstop work just to analyze a single pipe system. It was that hard. Okay, so to really get why the pipes are bent, we first have to understand what they're up against. Every single pipe is in a constant battle with these invisible forces that are always trying to push, pull, and break the metal from the inside out. The number one enemy, the biggest culprit of them all, is something called thermal expansion. It's simple, really. When you pump hot stuff, like steam or oil, through a pipe, the metal heats up, and when metal gets hot, it expands. Now, if that pipe is locked down tight at both ends, it has nowhere to go. So it just pushes, and it pushes with an unbelievable amount of force. Enough to crack concrete or completely wreck super expensive machinery. It's the exact same reason you see train tracks buckle on a hot day. And it's not just about the heat. You've also got the massive weight of the pipe itself, plus all the liquid inside. Then there's the internal pressure that's trying to make it burst. On top of that, you've got things like high winds or even earthquakes. And don't forget about vibration from pumps shaking or just the fluid sloshing around. It's basically a non-stop attack from all sides. And a lot of these forces, they come and go. A plant heats up when it starts and it cools down when it stops. That cycle of expanding and contracting over and over puts a ton of stress on the metal. It really is like stretching a rubber band again and again. You know what happens, right? Eventually it gets weak. We call it fatigue, and it just snaps.
So how do you stop that from happening? Well, this is where a chart like this comes into play. You can think of it as an engineer's crystal ball. It tells them exactly how much stress a certain type of metal can handle and for how many cycles before it's in danger of failing. This is literally how they make sure a pipe that's supposed to last for 30 years actually lasts for 30 years. All right, so you've got all these forces trying to destroy the pipe. How do the engineers fight back? Well, they don't try to just overpower the forces. They do something way smarter. They use geometry. Let's take a look at their secret weapons. The first and most important strategy is actually to not fight the expansion at all. You just let it happen. Instead of trying to build some massive anchor that can hold back 1,000,000 pounds of force, you just give the pipe a safe way to move. And this is a perfect example of what I'm talking about. See that big loop? That is not a mistake. It's an engineered spring. By adding those extra bends and all that extra length, the pipe gets flexible. So when it heats up and grows, instead of pushing against its anchors, it just flexes into the loop. It absorbs all that movement safely without creating crazy amounts of stress. Those bends are there for a reason. They turn a stiff pipe into a spring. But okay, you can't just let the pipe flop all over the place. That would be a disaster. So the second big strategy is all about control. You let it move where it needs to move, but you hold it steady everywhere else. And to do that, engineers have this whole toolkit of specialized supports. You've got things like spring hangers that hold the pipe's weight but let it move up and down. You have guides that let it slide back and forth but not side to side. And then you have stops that are like a brick wall. No movement in that direction, period. It's this really complex dance between freedom and restraint. So you add some flexibility. You add some supports. Problem solved, right? Not even close. This is where things get really, really tricky. It's an incredibly delicate, high-stakes balancing act. See, if you make a pipe too flexible, if you add too many loops, it can get, well, flimsy. It might start to shake violently, or all those extra bends could cause the fluid pressure to drop, which makes the whole system less efficient. You have to find that perfect middle ground. But honestly, here's the biggest challenge of all, what they call system operability. The pipe itself? It's usually pretty tough steel. The real danger is the force that the pipe puts on the equipment it's connected to. We're talking about multi-million-dollar pumps, turbines, vessels, and they are very sensitive. So the hardest part of the job isn't just saving the pipe. It's designing the pipe so that its own movements don't destroy the very equipment it's supposed to be feeding. And just to give you a sense of the scale we're talking about, get this number. A modern nuclear power plant can require 2 million man-hours of pipe stress analysis. 2 million. That is just an insane amount of engineering to make sure every single pipe is doing its job safely. And none of this is just engineers making it up as they go. Every single decision is guided by this strict hierarchy of rules. It starts with national safety codes, then it goes down to project-specific rules, and all the way down to what the plant's owner wants. It's an incredibly rigorous and layered process. So, how did we get from this being a mysterious subject that only a few people understood to being able to do 2 million hours of analysis on a single project? Well, the answer, no surprise, is the computer. It's what turned this dark art into a full-blown science. The difference is just staggering. Back in the 60s, you'd have one guy spending 2 solid weeks analyzing just one pipe system by hand. Today, a computer can analyze an entire plant with thousands of pipes in just a few minutes, and it does it with way, way more accuracy than was ever possible before. The technology that makes this all possible is called the Finite Element Method, or FEM. And the idea behind it is actually pretty brilliant. The computer takes a really complex shape, like a whole network of pipes, and it breaks it down into thousands of tiny, simple little pieces called elements. It can solve the math for each tiny piece really easily, and then it just adds all those results together to get a super precise picture of all the stresses across the whole system. Now, after all of this, after all this complexity and millions of man-hours, the source material says something that's kind of surprising. It says that because steel is so tough, the piping will work most of the time, even without going through proper stress checks. And that kind of leaves us with one last question, doesn't it? When we're talking about the systems that power our entire world, the pipes that carry our fuel, that make our electricity, that create the materials for our modern lives, is most of the time really good enough? The genius of the bent pipe is the answer to that. It's all that silent, hidden, complicated engineering that makes sure our world doesn't just work most of the time, it works all of the time.